Welcome to week 10, lecture 2 of this NPTEL course on muffler acoustics. The last lecture of this week, we just sort of set up the equations required to analyze a network connection, that is a connection in which waves can travel through different paths, that is the waves can travel through, say for example, this path and this path. We set up the different equations and kind of figured out that simple cascading of transfer matrices can't be really used. One has to resort to write down the different equations that characterize each element and the junction laws itself, and then assemble all the things into one big matrix like the one that we are seeing here, and this is represented in terms of the variable that is pertaining to the downstream ones. Okay. So, this matrix needs to be inverted and then multiplied, alright. So, what we are going to do in this lecture right now is basically to do two things. First of all, for such simple elements like the one that I have considered, this one, we have this kind of a thing. So, between this point and this point, what we figured out was that although it is complicated, we can sort of develop an analytical formula at least for the two duct system. Then there are a bunch of papers which talk about modified Herschel-Quincke tube, in which cases you have things like even more tubes attached. For example, things like this one, okay, things like this one. So, they are basically like 1, 2 and 3 pipes, or they could be more, they could be things like this one, So, there could be n number of such pipes, each with different lengths, and the constructive or destructive interference causes resonances. So, let us actually get back to our simple configuration, that two duct configuration like the one that was presented here. So, what we can do is basically kind of develop an analytical formula for relating the upstream variable 1 with the ones that is presented, one that is mentioned here, that is 6. So, let us see how we kind of do it. We again have the junction laws, but what we could possibly do is that start let me draw this guy again. So, we have this kind of a thing, and we have this kind of a thing. So, of course, we assume that the pressure is uniform at this point. So, let us name this as 1, 2, 3, this is 5, 4 and 6. Okay. So, we have your P1, I am dropping the tilde sign deliberately, P4 is equal to P5 is equal to P6, and V1 is equal to V2 plus V3, V4 is equal to V5 plus V6. Okay. So, we have this kind of a thing that we already saw in the last class. So, what we do basically is that we have also the other representation, that is the transfer matrix representation, where P2 V2. So, this is, I would just put it at C2, that is basically C. I will tell you what it means. And another thing that I kind of forgot to mention, this is Y naught, this is also Y naught, meaning that cross section area is the same for both the things. So, this is let us assume the diameter is D naught. Okay. So, this is your J Y naught into S2, J Y naught S2 C2, and here you have your P5 V5, here you have P3 and V4. So, here you have your C, let me call it 1, J Y naught S1 C1 P4 like this. So, we have this kind of a thing. Okay. Now, one needs to combine all these things to ultimately get P1 in terms of P6 V6, as we have already discussed. So, how do we go about it? First thing, right now our focus is to quickly develop an analytical formula using some of these expressions and possibly going to MapleSoft, and then trying to write down a clean expression for the transfer matrix between the upstream and downstream variables, and then get some basically figure out where the resonances or the troughs would occur based on the constructive or destructive interferences respectively, and validate that using a network analysis. All these things will be done in the computational part will be done in MATLAB after we have developed the analytical formula by aid of Maple. So, now let us go to the let us say this is a bunch of equation 1, 2, 3, 4, 5 and 6. Now, first let us see V 1 is equal to V 2 plus V 3. So, from this thing we can get V 2 in terms of P 5 V 5 and V 3 in terms of P 4 V 4. So, we can straight away write V 1 is equal to what? J S 2 Y naught, okay, into P 5 plus C 2 into V 5 plus your J S 1 Y naught P 4 plus C 1 into V 4. Okay. So, we have this sort of a thing. Now, we again invoke the relation here, equation 3, where P 4, P 5 and P 6 they are all same. So, what we can do is that we can just take J Y naught common, and S 2 plus S 1 will be common, and this will be P 6, and C 2 V 5 plus C 1 V 4, where C 1 C 2 again I am reminding you they are not constants, they are your cos k naught L 2 and cos k naught L 1 respectively. Now, we have this kind of thing, I am making it a dashed box expression because this is not the final one. Okay. So, now another thing that we can also notice from this set of equation is that we can express this guy V 5 in terms of V 2 and P 5 or P 6, or rather P 2 which is basically P 1 and P 5 which is basically P 6. So, eventually V 5, that is the velocity mass velocity that comes in this pipe, can be expressed in terms of the pressure here and pressure downstream. So, that is what we want. So, this can also be written rather cleanly. So, that is P 1 minus C 2 into P 6 by J Y Y naught into S 2, that is your sine, is equal to V 5. Okay. And your V and similarly P 1 minus C 1 P 6 by J Y naught S 1 will be equal to V 4. Okay. So, these two guys can straight away be substituted in this equation. So, it is going to be a little algebraically a bit messy, but that is the way with, the things are with your network system. So, J Y naught into S 1 plus S 2 times P 6 plus C 2 times P 1 minus C 2 P 6 J Y naught S 2. Okay. And your this thing will become C 1 P 1 minus C 1 P 6 J Y naught S 1. Okay. So, we get this. So, we can sort of again tend to simplify these guys. So, what will we get? We will get J Y naught into S 1 plus S 2, and P 6 is with this thing. So, it becomes minus C 2 square by J Y naught S 2. So, note that this is a minus. So, this will can be written as plus J square. So, this will be plus J. Okay, minus J square is just J, minus 1 is just J square. This can be simplified further, and plus you also have your J C 1 square by S 1 into Y naught. The entire thing is multiplied by P 6. Okay, that you get. Now, plus you have your J Y naught, and you have your J Y naught can be taken common, and C 2 by S 2 and your C1 by S1 and this is P1. Okay. So, we are going to get these expressions. These can be of course be further kind of simplified, and what we can do possibly is that we can tend to write these guys as V1 minus 1 by j y naught into C2 by S2 and C1 by S1 into P1, and this is equal to the big expression here. I am not going to bother writing this thing again, but perhaps just mention this thing here, that this is j y naught into your j y naught can be taken common, and S1 plus S2 and plus the other guys, and this is equal, this is multiplied by P6. Okay. We have this kind of a thing expression, okay, and then you need to invoke another such identity for doing the analytical derivation. So, what do we do? What is the other identity that we have? This is of course one of it. What is the other one? V6 is equal to V4 plus V5. Now, V4, V5 we have already kind of figured out from the slides here. So, this is basically when we invoke such a thing, we are using really your the expressions here. Right now we use the things here, now we are using the things here to get another equation. Okay, remember we in this equation we have 3 variables V1, P1 and P6. We need another equation so that we can have something like A matrix times P1 V1 is equal to B matrix times P6 V6, and then we can invert it. Although it is going to be quite messy, we are going to go to Maple and get our stuff done. So, once we substitute these guys in here, this equation and this equation, what are we going to get? We are going to get, after a bit of a simplification, well, let me just write it down, P6, and this will be j y naught S1, and this will be P1 minus C2 times P6 by j y naught S2. So, V6 is equal to j y naught by 1 by S1 by 1 by S2 times P1 and minus P6 j y naught, and your entire this one will be C1 S2 plus S1 C2 and S1 S2. So, we have this. So, what we could do is basically get these guys in here P6 j y naught. So, this will become your sine of k naught into L1 plus L2 times S1 S2 is equal to 1 by j y naught times 1 by S1 and 1 by S2 times P1. So, you have another such relationship. Okay. So, we have got this star, we have got this double star. So, we can obviously write it in the form something like I was mentioning, A matrix, A sum matrix and P1 V1 is equal to B matrix times P6 and V6. So, based on our convenience, we can do either do A inverse B, we can get the total or overall transfer matrix from upstream to downstream, or we can, if you want to explicitly relate downstream variables in terms of upstream variables, so we can do B inverse A, that is the inverse of the transfer matrix. So, what I suggest is that we can quickly go to Maple, and because this is going to be algebraically a bit tedious. So, what we can do is that we can go to Maple and figure out things. So, we have opened Maple, and in Maple there are some codes that I have already typed. We did this thing in sometime in week 5 where we are doing some conical ducts and stuff like that, and also in the weeks before week 5, like probably week 4 or something like that, when we did extended inlet and outlet mufflers for the first time. So, we do restart as usual, and we do linear with linear algebra, and we kind of introduce these things. So, T1 is a matrix, we will it's a 2 cross 2 matrix, and J is your root over minus 1, and what we need to do is that if we go to our presentation, we will realize that this is the j y naught and 1 by S1 plus S2. So, this can be written as S1 plus S2, and another equation that we have is basically your this guy. So, here will be minus 1 by j this thing. So, in the numerator you will have your sine of k naught into L1 plus L2, and in the denominator you have S1 and S2, and so this will be, there will be a minus sign associated here, and this will be 1 here, and similar things exist here. So, basically after I am kind of avoiding the going through each and every step, but I am just trying to present to you the entire thing. So, here we will get your T1. So, let me just uncomment this. So, T1 is this thing. So, T and this is like this. This guy will be your this thing, and this will be this thing. So, we get this T1 matrix something like this, and then your T2 matrix is also defined like this, and you have basically this kind of a thing. Now, I can just uncomment this guy and just say cos of k naught into L2 and all these terms. So, these are really your kind of transfer matrices. So, these are basically your transfer matrices for the tubular elements 1 and 2, not the A and B matrices. So, and the vectors are your basically for your downstream variable, that is your basically your I guess P5 V5 and P4 and V4. So, let us define it. So, this is P5 V5 we have initialized. Now, what we do is basically multiply. So, vec 3 is nothing but your, so this will once you multiply the first transfer matrix with this one, you will get your the relation, that is your, I guess you are expressing P3 and V3 in terms of P4 V4. Okay. And similarly in this you are expressing P2 V2 in terms of P5 and V5. So, then what we do is that we substitute in place of P4 and P5 P6, that is what we have done here, and vector 3. So, we have substituted this in vec 3 2 1, 2 1 means the second row and for vec 3 and second row of vec 4. Why are we doing this? Because as we realize first it is V1 is equal to V2 plus V3. So, we are getting V2 and V3 in here, and then we are doing all this algebraic manipulations. So, V1 is we are defining V1 like this here and substituting all this expression like the one that I talked about, and then we get this kind of a thing, and then further this is further I guess simplification. So, we get V1 here. Now, we can sort of collect the terms in P1 and P6 and then define a matrix. So, this is exactly the form that you saw somewhere in here, is not it? The only difference is that, well, V1 is equal to P6 and P1, you are seeing this. So, same thing we are getting here. So, we can avoid the hand calculation and go to Maple. So, we are defining M1 matrix and only putting certain entries like the one I talked about. M2 is 1 and M2, this is this guy I was talking about, and this is 0 based on this thing, based on the variables if they are present or not. So, M2 is again defined as M1 inverse because we need to relate upstream to downstream. So, we get this, and M3 matrix is something that we get because of the things in here, that is your the first equation. So, this will be having coefficients all that is mentioned here, and the coefficient of V6 will be 1. Okay. So, this is 2 cross 2 matrix, this is 1 again like this. So, we keep doing all this algebra, and then there is a command matrix multiply in Maple. So, we get this to finally get this TDS kind of looking expression. So, what it means is that the first, so this is basically nothing, but let me just go back to the presentation. So, eventually what we are successful in doing is P1 V1 is equal to some A inverse B. So, that is your P6 V6. So, I am calling this guy as T matrix times this thing. So, this is the upstream relation between upstream and downstream variables after a lot of algebra. This can be verified from the book on ducts and mufflers by Munjal, and also previous papers by Salamet and others where it was first discussed. So, let us get back to your Maple, and we figure out that M411 is nothing but sine of k naught L1 L2 and this thing, and this is nothing but S1 and S2, and this is the most tedious looking expression. We will worry about that in a bit. So, but other expressions are fairly simple in the sense that you have your M4 matrix here. So, M412, that is basically you have T11 figured out, T21 is a bit nasty looking thing, T12 and T22. So, what is T11 and T22? So, that is your basically j y naught into S1 S2 divided by S1 plus S2. So, S1 plus S2 is always common and we can just take it out of the matrix. So, and this is your minus j square. So, minus and into minus, that will become plus sine of k naught L1 plus L2 divided by S1 plus S2, and this is the expression that that is present here is given by M421. Once you kind of simplify this expression, so after some standard algebra, so what you will figure out is that this expression can be straight away written in the following form, and you have your S1 and S2 also in the denominator. I am sorry, which is basically here. So, and the numerator is this thing. So, basically what happens is that this expression, when you simplify the entire thing, this guy will become T21 will be equal to j y naught, and of course, in the denominator there will be S1 plus S2, and in the numerator there will be 2 times 1 minus cos of L1 plus L2. Okay. So, you will have this kind of a thing. Okay. So, what we can do is that quickly go to MATLAB and figure out things, but before that is an important thing to mention here is that you have in the denominator S1 and S2. Okay. And so, what does it mean? It means that once you have related upstream variables to downstream variables. Now, if you were to do the opposite, that is relate downstream to upstream, clearly S1 and S2 will occur in the numerator, that is P6 V6. If you write in terms of T inverse, you will get P1 V1. Okay. Now, this guy, because this is S1 plus S2 term is in the denominator for the T matrix, in the numerator it will be on the when you invert this T inverse, it will be in the numerator. So, what does it mean? For transmission loss, P6 and V6 both will become identically 0 when S1 plus S2 is 0 for a particular frequency. That is the if you apply your anechoic termination and figure out the waves that go propagate in the downstream of the anechoic termination. So, that will be identically sort of 0 provided that your S1 and S2, that is your sine k naught L1 plus sine of k naught into L2 is equal to 0 for a given frequency, and such is the frequency where a destructive interference happens. Okay. So, let us go to that. So, when will that happen? When you have sine of k naught L1 is equal to minus sine of k naught into L2. This will happen when sine of k naught L1, there are two conditions of course. So, minus can be written as cos of 2 m minus 1 pi, because for any m is equal to 1, 2, 3 and so on, and here this will be 0 identically for all m being an integer. So, why the reason that I have written this is because this guy can be written as 2 m minus 1 pi plus k naught L2 is equal to sine of k naught L1. Okay. So, you get your k naught L1 is equal to 2 m minus 1 pi plus k naught L2. Okay. So, what it means is that when k naught and k naught L1 is and k naught L2, the difference between them is really the path difference between the waves that come, path difference between the waves that arrive from here and the waves that propagate here. When this path difference is equal to 2 m minus 1 times pi, where m ranges from 1, 2, 3, 4 whatever it is, some integers. then you have your destructive interference, and then your S1 and S2 is cancelled. So, this is one relation that we have. Now, another way in which the destructive interference can happen is when KL2 is equal to 2n pi minus K0 L1, that is K0 L2 plus K0 L1 is equal to 2n pi, where n is equal to your 1, 2, 3 and so on. This is what you get. How do we get this guy? Because here, just like instead of minus I have put cos here, you can actually also do it the other way around. So, this will happen when you take minus inside. So, what you can get is basically sine of K0 L1 is equal to sine of minus K0 L2 plus 2n pi, where your K0 L1 is equal to 2 pi into n minus K0 L2, where n is equal to the same thing here. Okay. So, this basically this relation will fetch you this one, and so basically what it means that when the sum of the phases of the waves that propagate in both the ducts is equal to 2 n pi, where n has to be 1 at least to make it non-trivial, then also destructive interference will happen, and then we will get almost 0 power transmitted downstream, resulting in sharp attenuation peaks. So, the frequency corresponding to this is easy to work out. So, this is 2 pi f I would say f p C naught, and this is 2 n pi and L1 plus L2. So, 2 is cancelled and so is pi. So, giving you f p is equal to C naught and of course, n times L1 plus L2. Okay, you are getting this relation for the corresponding to this condition. What about the other condition? So, other condition will fetch you the following relation. So, this is your f p is equal to 2 m minus 1 by 2 into C naught into L1 minus L2 or L2 minus L1, depending on whichever is greater. M is 1, 2, 3, 4. So, we can work out a couple of interesting cases. So, what we can do is that for the configuration that I have shown here. So, what we get really is that suppose we take this length to be 0.5 meters, that is about 500 mm from here to here. Okay. And this guy is about just half this thing. So, it becomes pi 2 pi r. So, it is just pi r. Okay. So, pi r means pi d by 2, and this is your 500. So, 0.5 by 2, that is pi into 0.25 and 3.14 into 0.25, and that sort of works out to be 0.7854. This is or 785.4 mm. Okay. So, we get this kind of thing. So, we can substitute these L1 L2 lengths. This is L2, this is L1, and the diameters, you can consider this something like a nominal diameter 40 mm or so. And now we can quickly go to MATLAB and figure out what is going to happen at the transmission loss. So, here we have your MATLAB script that I have written in advance. So, I am not going to do it live here. These codes were written some time back. So, I am assuming the sound speed of 346 here, and diameter is something that is given by the user. L1 and L2 are the lengths, as I have mentioned. This is the characteristic impedance. So, this is the connectivity matrix. What I am going to do is that I am just going to comment out the entire thing here, that much I can do, and just use the analytical expressions, the one that we derived in Maple, using the help of Maple and some simplification. So, these are nothing but sine of K0 L1 plus L2, your T11 parameter, this is J Y0 into sine of S1 S2, this is your again S1 sine of K0 to L1 plus L2, and this is nothing but the simplified expression, and denominator is this one. So, we divide the entire matrix by this. So, once we get this, then these things, this particular function is invoked by the transmission loss function, which is invoked by the transmission loss plot. So, what we are going to do for the parameter range that I talked about, I can just set this to be 40 mm, and length can be 500 mm, The other guy, like I mentioned was 785.4 mm. Everything is in meter. So, I can go from 1 to 3000 hertz, because really for such things only very low frequencies will propagate. So, we have this kind of a thing. So, it is going to take little bit time and we get this kind of a transmission loss. So, what is important here to note is that let us first analyze 2 or 3 important peaks that would kind of occur. We will go to the basic data tip. So, we get your 269 at frequency 269, we are going to get one peak. Another peak that occurs is at 538, next one that occurs is at 606, and so on. We can easily do the maths, I mean in the sense that if we figure out like m is equal to 1. So, 0.5 times 346 and the denominator will be 0.7854 minus 0.5. So, let us analyze where do we get 606. Okay. So, this is the first peak that we are getting due to destructive interference, and what about the other one peak due to the other term. So, that is basically your C naught, that is your 346 divided by L1 plus L2, and n is 1 in the other formula, that is 269. Okay. So, you are getting a peak at 269, okay, and the other one is probably the multiple of that, which is nothing but if you just multiply the numerator by 2, you should be fine. So, this is 538 what we are going to what we are getting. So, like this we can completely cover the entire thing. Now, we can basically figure out why these peaks are occurring wherever they are occurring. Now, another way to basically compute this is using a connectivity matrix approach. The analytical one I talked about because I want to demonstrate, as is usually the case with all courses in science, engineering, that you consider whenever you develop a new kind of an approach. We tend to develop we tend to consider a system which is only slightly more complicated than the usual one, so that at least somehow you can get a feel of the analytical formula. So, that is what we have done here. But for much more complicated systems, like I will talk about that, I will draw that and probably show you some figures, some muffler configurations published in previous papers. So, in such configurations it is almost impossible to figure out the transfer matrix, that is overall transfer matrix between upstream and downstream variables analytically like we have derived here. So, we have to go to the connectivity matrix approach. So, it becomes quite important that we kind of go to the use the connectivity matrix approach and demonstrate that it works very well even for I mean just to begin with for such a system. So, we are going to comment out the entire thing and I am just going to walk you through the code. I encourage you also to start coding. It can be any language, not necessarily MATLAB. So, we define a connectivity matrix like 10 cross 10 where remember we want to invert A inverse B. So, we are getting the C matrix and we are taking only a chunk of that is only first few rows to get stuff. So, this is your 10 cross 10 matrix, and here this is your first row is your first P1 is equal to P2, P2 is equal to P3, that kind of relation. Then is the mass velocity conservation equation, and then this is the relation between your variable from 2 to 5, the tubular element. So, let us go back to the code. So, that is what we have done in rows 4 and 5, and then similarly rows 6 and 7 we have related things for the straight thing, okay, and then your junction loss P4 is equal to P5, now P5 is equal to P6, we can easily get that, and this is your mass velocity V4 plus V5 is equal to V6. And similarly vector, this thing will only be initialized with 10 cross 2 system, but with zeros, but only a few entries, couple of entries in this case will be non-zero, and that will be your P4 is equal to P6 and V4 plus V5 is equal to V6. Then it is as simple as sort of inverting, writing a command solmat, that is basically your C matrix is A inverse B kind of a thing. So, we get this. So, in practical system this is 10 cross 10, it can be 10,000 cross 10,000 also. So, this can be pretty challenging, and then we take only the first two rows because remember it is also about proper bookkeeping. So, we might, so one possible area of, one possible area of research is to develop an algorithm which will just see the stuff and it will put, it will define the connectivity matrix in such a manner, start dumping the elements at appropriate places using proper bookkeeping. So, these are all part of numerical techniques or training that one must go through. So, T1 and T2 we are getting like this solmat, and then the idea is just to run the code again. So, I have already put hold on means save the previous result and plot it using a different color. So, right now mind you I have commented out this part, and I am going to just use another color, say black K, and plot. It is going to take some time, 0.94 seconds. Where has it gone? Well, it is almost identical, it is identical. So, this is the numerical way of doing stuff, it matches very well with the analytical formula. Same thing I will not repeat again. So, this is I have taken out and pasted it again. So, we are getting multiple resonances due to destructive interferences, and there are some troughs also occurring because of constructive interference. There are frequencies at which the entire acoustic power is transmitted as it is. So, these are all part of multiply connected mufflers, and then there are large number of such connections. For example, what I am going to probably talk about in the next class perhaps is some few connections which are much more intricate, much more complicated. So, till that time, goodbye, I will see you in the next class. Thanks.